This is mind-blowing. Imagine a single cloud of atoms that flows without friction, yet arranges itself into a crystal lattice at the same time. But here's where it gets controversial. Does this shape-shifting blur the line between liquid and solid, or does it redefine what we call matter? In our everyday experience, materials fit neatly into gas, liquid, or solid categories. Quantum mechanics, however, plays by different rules. When atom clouds are cooled to just a hair above absolute zero, their individual identities fade and they merge into one coherent wave. Physicists call this a Bose-Einstein condensate, a superfluid that glides without any resistance. The Synthetic Quantum Systems Group at Heidelberg University, led by Professor Dr. Markus Oberthaler, has now demonstrated something extraordinary. By feeding a whisper of energy into a superfluid, they observe sound waves traveling at two distinct speeds through the same atomic ensemble. One wave disturbs the fluid component, while the other shakes the emerging crystal pattern. This dual behavior is the signature of supersolidity, and their results are published in Nature Physics, August 2025, DOI 10.1038 S41567-025-029274. And this is the part most people miss. Supersolidity doesn't appear at room temperature. Only under ultra-cold conditions do atoms behave like overlapping waves rather than individual billiard balls. In that regime, particles lose their separate identities and move as one, much like a stadium wave where each spectator rises and sits in unison. Under the right drive, periodic density ripples form within the superfluid, giving it a crystal-like structure without destroying its frictionless flow. Picture shaking a cup of coffee. Ripples appear on the surface without turning the liquid into ice. By rhythmically modulating the interactions between atoms, the Heidelberg team created a dynamic, non-equilibrium quantum system that both flows and solidifies. Previous experiments had hinted at crystalline patterns in driven superfluids, but no one had teased apart the two sound modes. Oberthaler's group used precision pulses to excite each oscillation separately and tracked the resulting defects as they moved through the atom cloud. The fact that these disturbances traveled at two different speeds confirms that the same system carries fluid and solid characteristics simultaneously. It's fascinating to see that a small energy kick can turn a superfluid into something that vibrates like a solid. Oberthaler remarks, as a sound wave passes, atoms oscillate around their equilibrium positions, just as they would in a crystal lattice, all while remaining part of the same coherent quantum wave. Nicholas Leadster, a member of the group, points out that this is the first time supersolid sound waves have been observed far from equilibrium. Typically, supersolids are discussed in static equilibrium terms, he explains. By shaking the superfluid and injecting energy, we've proven that supersolidity persists and even thrives outside those calm conditions. Is it fair to still call this a solid when it slips and slides like a liquid? Some argue that the term supersolid stretches the definition too far. Could these hybrid phases deserve an entirely new category? What do you think? Does this discovery upend our textbook categories, or is it just a quirky quantum oddity? Share your perspective and let the debate begin.